according to this standard minimal, say, Fermi theory. And this theory is not renormalizable. This means that when you compute radiative corrections using this Hamiltonian, you will find divergences, and you will not be able to systematically remove these divergences like in electrodynamics. This is what you will study later. So this is actually another argument that probably this is kind of effective theory which should be substituted by some more fundamental theory later. So nowadays people are introducing also effective operators of interactions with many fields. You can introduce, say, many fields, 6, 7, whatever it is. But again, that will be non-renormalizable, and the idea that probably this comes from some more fundamental theory. Now, today's lecture will be devoted, so we are continuing to discuss cross-sections and number of events and discoveries of neutrinos. This is what we have started before. As a consequence of Fermi theory, new processes have been predicted beside the beta decay, and one of these processes is inverse beta decay, when antineutrino interacts with proton and transforms a transformed proton into neutron, and then transforms itself into positron. So these are the same particles as in the beta decay. We just permuted some particles from initial to final state. This is what we call algebra of reactions. So therefore, the same Hamiltonian is responsible for such a process. Okay? So this process has been suggested as a possible test of existence of neutrinos. And remember, to establish that neutrino is a real particle and not kind of dynamical phenomenon, you need to find interactions of these particles somewhere outside of production region. So that's important process, because you have protons, you can have a target with hydrogen, and then to study this process. So let us compute cross-section of this process. At energies of neutrinos, say about 3 MeVs, 3-5 MeVs. Those are the energies which were used to discover neutrino, and these are typical energies from beta decay. Okay. Now, you haven't studied field theory, you haven't computed any probabilities and cross-sections. Nevertheless, I will show you how we can still do and compute this cross-section. So the process is, again, let me depict this Feynman type diagram. Is antineutrino, positron, proton, and neutron in final state. So, and we assign these arrows to fermionic fields, and for antiparticle, we assign this in opposite direction. I will just use standard notations, but for you it is just important that in initial state we have antineutrino and proton, and they are transformed into positron and neutron. So essentially, we can consider the scattering of antineutrinos on nuclei which contain proton. And then you produce positron and a neutron in final state. And the proton is sitting here if it is neutron. Now, how to compute cross-section? Do you have some idea? By the way, what we should do is the following. We need to compute sigma, which is proportional to moduli square of the amplitude of this process. In quantum mechanics, we are computing first amplitudes and then compute moduli square. Oh, I have forgotten to switch on this stuff. Or it's switched on. Okay. And this is nothing but moduli square of the matrix element between final and initial state, right, according to quantum mechanics. By the way, the question why Hamiltonian is the operator which actually gives the amplitudes of transitions and then probabilities eventually. Why we use Hamiltonian operator?
Because it generates the time.
Yeah, so because Hamiltonian describes evolution of the system in time. And so this is why we are computing the matrix elements of the Hamiltonian. So what is our initial state? Our initial state is antineutrino and proton. And final state is positron and neutron. So we need to compute this matrix element and square it. Well, I have here proportionality sign, let me put it in this way, because you need to take into account some kinematical factors, essentially phase volume, and then make integration over the phase volume. Have you learned something about phase volume? So essentially you have two particles in final state, and cross-section, to compute cross-section you need to add these factors, which is the momentum of positron and then free momentum of neutron. And then you make eventually integration if you are interested not in differential cross-section but in total cross-section. So that's kind of involved problem, right? So you need to compute these matrix elements. You need to take into account spinors because these are fermionic particles. They have these degrees of freedom. The only what we can say immediately that this cross-section should be proportional to G Fermi squared, right? Because our Hamiltonian is proportional to G Fermi, and this is constant just for our energies. So we can put it out and then square, and this is G Fermi. Now what I will show you the power of so-called dimensional analysis and dimensional consideration. When we can actually get almost complete answer without really doing any computations. And this is very important tool in particle physics, and we are using this dimensional analysis, and I would advise you to do this in the first place, and that before even you are doing detailed computations. So you may spend, say, 1 day to make computations of this process. Well, if you have experience, you may probably do this in few hours. But you will do this just in a few minutes. So, the important feature of the process, and we are dealing here with energies of neutrinos, as I said, 3-5 MeVs, is the following. This energy is much bigger than the mass of electron, which is 0.5 MeVs. And this is much smaller than the mass of proton. Right? This is our target. And we will use this. So, of course, it's not just dimension, but we are using some kind of features, kinematical features of the process. So first cross-section is proportional to G Fermi. Square. Now, that should be multiplied by something, all right? And we are computing total cross-section of this process. So what is dimension of this X? This guy has dimension centimeters squared, which is 1 over mass squared. G Fermi has dimension 1 over mass squared, and square will be 1 over mass to the fourth. And therefore this X should have dimension of mass squared. Agree? Okay. So eventually, cross-section should depend on parameters of our process, right? What are quantities which have a dimension of energy? The quantities are, in our case, the energy of neutrino, then the mass of electron or positron, then the mass of proton, or mass of neutron also, which is kind of close. So which means that this M eventually should be cooked out of all these quantities which are available. So there is no way to get something else. So that's what is available, and we need to construct this X out of these quantities. Now, since energy of neutrino is much smaller than mass of the proton, in the first approximation we can use an infinite limit for the mass of the proton. So which means that this mass should not enter this M. On the other hand, the energy of a neutrino is much bigger than the mass of the electron. Therefore, in the first approximation, we can put mass of the electron to be 0. And so, the only quantity which is left is the energy of neutrino, right? And therefore, we can identify X with the energy of neutrino, and then write our cross-section as G Fermi squared, energy of neutrino squared. Except for some special cases, this type of the arguments work. I will show you later some exceptional case where this consideration fails. But in the most of the cases, this works. Of course, you will get some corrections onto finite mass of proton, which means doing this, we neglect recoil of protons. So this limit corresponds that our scatter is very heavy, and therefore recoil can be neglected. So this is the physics of this assumption, which is kind of very good approximation, because energy of neutrino is 3 MeVs, and the mass of the proton is 900 MeVs. So which means that you can expect some corrections, at least like 1 over 300. Here is a little bit less kind of exact, because mass of the electron still say factor of 5, 10 smaller. But in the first approximation, you can also neglect the mass of the electron. Now, what is amazing, that exact quantity for the cross-section is G Fermi squared, energy of neutrino squared, and then the factor 1 plus 3GA squared over pi, where GA is so-called axial vector coupling, and it equals 1.23. This is axial vector coupling. So, if you insert this quantity then you will get that this additional factor is approximately 4/3. That's approximately 1.33. So, which means that using just dimensional arguments, we managed to compute cross-section with accuracy, say this 30%, up to this factor, 1.33. Now, this is, this factor GA actually takes into account even parity violation. So that is a computation made of correct structure of currents. Remember, we discussed that in original Fermi theory it was just vector currents. But indeed, then parity violation has been discovered, and therefore true current has structure vector plus or minus axial vector coupling. And axial vector coupling, it was some question, comes with this additional this is 1.23. We will discuss this later. Questions?
In the real value, there's no contribution from energy of the mass of the bottle and.
Yeah. So here are some other factors. I didn't put this. Again, some factors which are say 1 plus O. Here is m of the electron, energy of neutrino squared, and even smaller factors which are yes. Actually, with this you can restore. And there are also tricks, and experienced people who made the computations can actually predict what should be the power of pi here. And power of pi here comes from a phase factor, which I have written. So remember, you need to take matrix elements squared and then multiply by the phase factor, which is 1/2 pi into some power. So once you know how many particles in final state, you can immediately say what is the power of pi, and then you make integration, also some pi disappear. And so even this can be actually traced. Well, even this factor I can also say that should appear, by the way. More questions? You see, it is important to always do this type of the computations before you will really start to do some lengthy and exact computations. Useful because you eventually will control your final results with, say, simplified analysis. And this is not a joke. I mean, that's the physics. And let me make a general comment of the following type. What we are doing is the following in quantum field theory. In QFT, we start from Hamiltonian or Lagrangian. Then using quantum field theory rules and do computations, and eventually we come with sigma, which is cross-section, or decay rate, or the probability. So these are the quantities we are computing. These quantities, in fact, are functions of kinematical variables and coupling constants which enter Hamiltonian or Lagrangian. So, for instance, cross-section eventually should be expressed, or this is a function of momenta of particles which participate in the process, their spins, and coupling constants. And let me put here J, which is coupling constants, which enter Lagrangian. Nothing more. So eventually, what we are getting is some function of these kinematical variables. So you can use straight way, without doing these lengthy computations, to find these functions of momenta, spin, and coupling constants, which is quite simple. Like here is coupling constant, it's just, you put this out of your moduli squared, so you can see this immediately. You can compute almost precise and completely, and in fact in the recent years it was a big development how to do computations, even high order computations, without really computing Feynman diagrams, using the tricks which I have used here, but also so what I have used here is kinematics, right? Kinematic properties, features like what is the mass of the particle. We eventually neglected the masses of electron and didn't consider it proton mass. So you can use kinematics. Symmetries. I did use here the symmetry, but what is interesting that you can look at your Lagrangian. Lagrangian may have some symmetries. And then already this tells you what should be functional dependence of your final answers. And we will discuss this when we will consider parity violation, for instance. So this is very powerful. This is why it is important to study the symmetries of your theory, symmetries of Lagrangian. Symmetries allow you, to a large extent to find these cross sections and probabilities, but also connect probabilities of different processes. This is power of the symmetry. And of course, one of these important symmetries is Lorentz invariance. And finally, we use dimensional arguments. So, using these tools, you can make quite precise evaluations of the cross sections. Now, questions. Again, this is one of the examples. We will also discuss some others. Actually, many derivations, which I will present here, since you haven't studied yet quantum field theory and various things. So I will do in this way, using the symmetries, using dimensional arguments, and some other tricks which I will show you later. This is useful. This is useful too. When you are a professor, when you become professor, you are just doing this, and then postdocs or students make precise computations. So yeah.
What makes us sure that, for example, the cross section is only with those parameters, or only can be expressed in only those parameters without any? Is it that the quantum field rules?
No, eventually you will get, what you will get is that your final quantities, observables, and you compute some observables which you can actually measure something, they depend on kinematical variables, on momenta of the particles, on the spin of the particle, and coupling constants. It is, I have no such a theorem, but this is what we are getting finally, right? So we are measuring momenta of particles, we are measuring the spins, and we are measuring intensity of the process, number of events. So finally we actually make our formalism in such a way to compute these things. If you want, this is our wish. We want eventually to have observables as functions of these variables. So we are not, in most of the cases, we are not interested, for instance, in detailed development in time, for instance. Then maybe some other quantities will be important. So what we are interested in is, we collide particles, and most of this formalism is actually adjusted for this. So we collide particles, we have some accelerator, right? Accelerate particle, collide, and then particles go out, stop to interact, they interact in some region. And so what are observables? We have free particles in the beginning, free particles in the end. which are completely characterized by momenta, spin, right? And so that's what we have. So our formalism is adjusted in such a way that we get some observable quantities which are functions of this. There are some other processes, like, and we will discuss this, like, for instance, oscillation processes, when we are interested not in asymptotic states which are just characterized by these, but also we are interested in development in time, for a given moment of time, what is the state of the system. Then we will discuss, we need to have to see some other observables. Okay. More questions, yeah?
What we estimate is the differential cross-section.
No, this is total cross-section.
Total. So, okay. And the pi factors comes from the integration of the phase space?
Yeah.
And that's
the
total cross-section.
Yeah. So, if you have differential cross-section, then you may have more pi's.
Okay.
Because if you want to have differential equation, then you may ask question, I want to select events with a given momentum of positron, right? Then of course then the energy of positron will enter. So this is for total cross section when you do all these integrations. Well, and the amplitude is usually like a 4 pi, then there's some factors and then phase factors. And these phase factors just depend on the number of particles in final state. And so you can compute easily what should be the degree of pi in final answer.
In principle, we can get also from these arguments differential cross-section, just adding a momentum of the positron there.
Yeah, but this is less trivial. Of course, then that's almost like explicit computation, right? Because then you need to make explicit computation on the phase volume, take into account energy momentum conservation. But again, some quantities can be computed in this way. Because what I used, remember, I actually eliminated all parameters of the energy dimension, but energy of neutrino. So that's how it works here. Okay. Now we are moving to discovery of neutrinos. This is a long story, and you will have exercise. Actually, I will give today later. I have prepared the exercises. Using this cross section, you can estimate what is the probability that neutrino interacts. You know, so if you take, say, device of the size of kind of reasonable 1 meter, then the probability is just negligible. You can compute using this cross-section the number of events. So you need huge amount of matter or very big neutrino fluxes to detect these events. And that has been clarified by Beta and Piles, and they did the first computations of this cross-section in 30s. And the conclusion was that most probably neutrinos will be never detected. So this is one of the examples. Be careful saying that something will be never detected and never seen. There were a number of developments before 50s when neutrinos have been eventually discovered or their interactions have been observed. And one of these very important developments was creation of atomic reactors, which of course people didn't thought at the beginning of 30s about this. So now we will discuss discovery of neutrino. And let me write that there are two key developments which led to this discovery. One is creation of atomic reactors. Which are very powerful sources of neutrino fluxes. So big fluxes of neutrino. And the second is development of new methods of detection of particles and creation of large scintillator detectors. So let me talk about these things, atomic reactors and then scintillator detectors. As well, so let me see. But before this, I want to actually introduce a number of events, how we compute number of events. Because this is what is important. You computed probability, cross-section. And then eventually you want to know what is the number of events you can observe. Suppose your cross-section is so small and your detector is not big enough so that you expect one event in 100 years. I don't think that you will be very much excited about this, right? Or in 1,000 years. You want to see something during your life, right? Or during operation of your detector. And nobody will give money for your experiment if you have so small number of events. So how to compute number of events? So let us consider again the detector, which is some volume with material of the length L and number density of particles of scatter n. And let S will be the area of the detector. So that's the size S. And we have incoming flux of neutrinos. This is how you want to detect neutrinos. Actually, this is general. You may speak on some other particles also. So, and you have flux of neutrinos. So we introduce the following notions. F, which is density of the flux. Density of the flux of incoming particles. In our case, those are neutrinos. So this is number of incoming particles which crossing unit of surface in unit of time. So F has dimension 1/centimeter² and second. So this is number of particles crossing unit of surface in unit of time. So for simplicity, I will consider uniform flux. You can, of course, imagine that flux can be different along this perpendicular direction. That will not complicate too much. But for simplicity, I will just consider uniform flux. And then total flux of neutrinos will be given by F multiplied by X. So this is total flux of neutrinos incoming or falling on your detector, right? What we are usually compute is the rate of events. So, which is number of events produced, in our case, neutrinos in the detector in the unit of time. So this is exposure time. Okay. So how we compute this rate? Rate equals P, probability of interaction of a single neutrino in our detector And then you need to multiply by F and S. This is total flux of neutrinos entering the detector. And then we just multiply by the probability that a given neutrino interacts in our volume. So that will give us the rate of events, rate of interaction of neutrinos in the detector. Agree? So this is probability of a single neutrino to interact in our detector. And then we multiply this by total number of neutrinos entering per second our detector. Now, what is this probability? We already computed it before. It's given by cross-section, number density of particles in detector, and L, the length of the detector. So this is the probability of individual neutrino to interact in the detector. And of course, I assume here that, that the probability is much smaller than 1, so neutrino has a chance only once interact in our detector. And then you multiply this by F and S. So ask me questions, because you will have some exercises to do this computation, then we probably will have better experience with this. Now here we have S, the area, and L. And L is the length of our detector. So that gives our volume of the detector, right? Volume multiplied by N gives total number of scatterers. And so we can write this as sigma, total number of scatterers, and the flux. Okay, so N, which is density, Ls, or N multiplied by volume, is total number of scatterers, or particles with which neutrinos are interacting. So very often you have, say, complicated material, and neutrinos are interacting only with some component of material. So this is total number of scatters with which neutrinos are interacting. So this is useful for us. So then this is our final expression. So the rate is given by cross-section multiplied by total number of scatterers and multiplied by the flux of neutrinos. Right? And so this is the rate. And then total number of neutrino interactions, or total number of events during the time t, is rate multiplied by t, exposure time. And that's given by sigma F, T, and then M. So from here you immediately see, to increase number of events, or the rate of events, you need to increase the flux and the size of your detector. So in the case of neutrino, that increase was due to atomic reactors. And that was because of this creation of big, relatively big scintillator detectors. Now they are enormously bigger than in the first experiments, but already at that time it was big enough to have a discovery. So that's new detector techniques. Detection techniques.
Atomic reactors here means the chain reaction that we...
Yes, yes, I will discuss this now. So there's big detectors, big detectors. big size of the detectors. And you cannot do anything about cross-section, of course. That's given. That's given by fundamental couplings. You may still kind of select certain energy interval. For instance, if you use neutrinos not from atomic reactors, but from accelerators, then sigma is bigger. Remember, cross-section is proportional to energy squared. It is energy square dependence up to, say, 1 GeV, but then dependence on energy becomes not so fast. The increase with energy, it's like a linear dependence. Questions? Okay, so let me discuss, give some information about atomic reactors and the fluxes of neutrinos produced by atomic reactors. In atomic reactors, what happens is fission of heavy nuclei, like uranium-235, uranium-238, plutonium-239, and plutonium-241. These are main components of the atomic reactor fuel. So fuel is made of this. In commercial reactors, mostly you have these three, a little bit less these, but there are research reactors of smaller size when they have almost pure uranium-235. So it depends on the reactors. So what's going on? Under action by neutrons, so you have medium with some neutrons, and it is an important component, which actually hit this nuclei, and then this nuclei split. So fission of nuclei occurs. They split into lighter nuclei in very different ways. So you may have a huge number of possibilities. In fact, almost 6,000 of different branches have been identified. Maybe they are even more. Okay? So that leads to energy release, and something like 200 MeVs is released in a single chain of the process. Because you have split, the nuclei can split, say, in two, then two others continue to split till they reach some stability band, what we are saying. So in this chain of processes, something like 200 MeVs of energy is released in the form of gammas, in the form of electrons and positons. But also neutrinos are emitted. So decays are mostly occur due to weak interactions, and so these kind of decays are beta decays. Okay. So why it happens so? Maybe you already see in this diagram number of neutrons. Here is number of protons in a given nuclei, and in this plot there is a stability band. Where you have nuclei with substantially large lifetime. Maybe seconds, maybe months, maybe years. So the bigger number of nucleons inside the nuclei along this island, so this is stability band. the more neutrons are in the nuclei. Of course, protons have repulsing forces, and so it's easy to pack with more neutrons when you go to bigger and bigger nuclei, right? So, and the forces which are keeping these nucleons in the nuclei are the strong interaction forces. So for equal number of protons and neutrons, you would have something like this. Along this line, you would have equal number of protons and neutrons, but you have this type of the band. Our nuclei, which we are discussing, are sitting somewhere here. So they are at this high mass end of this. When this nuclei split, what is formed is very unstable nuclei. So imagine that one of these guys split equally into two nuclei with equal number of nucleons. So then you are sitting here, so it's 1/2, and you have two nuclei which are sitting somewhere here, if you just divide by 2, right? Which means that you are out of the band of stability, and you produce nuclei which are overloaded by neutrons. So here you have nuclei overloaded by neutrons. So here on this side you have nuclei which are overloaded by protons. But due to fission, you are sitting somewhere here. But of course, you may have not kind of a split of nuclei, not onto equal number of nuclei with equal number of nucleons. You may sit down, say one is somewhere here, another one is here, so you have all kind of combinations. So bottom line, under action of neutrons, these nuclei split, and then they split more, and these guys split, so you have this fission process. What is formed are unstable or very unstable, because these guys are relatively stable. They are stable, so they start to split under action of neutrons. In fact, changing these fluxes of neutrons in your atomic reactor, you may change the power release, right? So you can shut down your reactor by removing neutrons, absorbing neutrons. So once you have this nuclei overloaded by neutrons, they will undergo beta decay, which actually reduce number of neutrons. And so the dominant process is that inside these nuclei, you will have the process which we have already discussed, which is electron plus antineutrino. So you will have process when you have nuclei with a number n and the charge x, and it will go to nuclei with a number n, number of nucleons, and this will be x plus 1 plus electron and plus antineutrino. So this is what happens inside this nucleus, inside this nuclei. There's one immediately important conclusion, is that in these processes you produce flux of antineutrinos. Antineutrinos, actually electron antineutrinos. I will discuss this later. We haven't introduced yet lepton number. So what is important to understand, we have neutrinos and antineutrinos, and here you are producing antineutrinos. And this is related to the fact that neutron go to proton, which means that the charge of nuclei increases by 1 unit, and then due to electric charge conservation, you need to produce electron, not positron, but electron. And then antineutrino because you have the conservation of lepton number. So in this way you conserve lepton number. So what is the flux of neutrino? You can compute flux of neutrino knowing what is thermal power of the reactor. So mostly people are using thermal or commercial reactors which produce power. I have written here already that about 200 MeVs is released per fission process. One can compute that per fission process, in average, you produce 6 antineutrinos. How you can compute this? You can compute this in a simple way. For instance, suppose, let's take this simple example when you have split into equal nuclei with equal or approximately equal number of nucleons, and then you can see how many beta decays should occur to reach this stability island or band, and this is approximately 6. You need to have 6 beta decays to reach this island in average. So then you can compute easily the flux of neutrinos as, let me denote this, I don't remember how it was actually denoted. Total thermal power of reactor over this, let me put here Q thermal, let me put here Q fission, and multiply it by 6. Right, so this is how you can compute the flux of antineutrinos. And numerically, this is given by 2 10 to the 20 neutrinos per second multiplied by power, thermal power, over 1 gigawatt. So if one says that I have reactor with the power, say 1 gigawatt, then it produces total flux to 10 to the 20 neutrinos per second. The 6 gigawatt multiplied by 6. And these days there are not only just single atomic reactor, but usually even the system of several atomic reactors. So it's really power can be easily say 15 gigawatts. Okay. Now what is the energy spectrum? To compute energy spectrum of neutrinos is really very non-trivial program. And the point I mentioned already, there are about 6,000 different branches of the decays. So in principle, you need to control, you need to sum up the spectra from all these beta decays. A huge number of different isotopes are involved. And you need also to compute what is the weight of different isotopes. The spectrum has typical shape of this type. It's decreasing spectrum. And so let me put here different quantities. So this is the flux of neutrinos as a function of neutrino energy. But this is actually not a smooth curve. You have very complicated structure here, which is related to summation of beta spectra from many isotopes. Now, what you usually see is the product of the flux of neutrinos multiplied by cross-section. So this is what you are interested in because you want to compute number of events. And as you remember, we computed cross-section. It has energy square dependence. So cross-section has such a dependence. And therefore, the number of events should have the dependence like this. So that is F times sigma. So this is number of events. It has maximum at about 3 MeVs. And spectrum of events actually continues up to, say, 8, 10 MeVs. So these are typical spectrum of neutrinos from reactors. So this 8, 10 MeVs. There are two methods actually to compute this spectrum. One is what is called ab initio. And why I'm discussing this in details, and the point is that these reactor experiments are extremely active these days. So maybe some of you who will do neutrino physics will meet this. So many experiments now running with reactors, atomic reactors. Another one is so-called conversion method. You see, in the beta decay, together with neutrinos, you produce electrons, right? So, in principle, you can measure the spectrum of electrons. Not in these big commercial reactors. I think nobody will even allow you to do this. But people are measuring this electron spectrum from, say, uranium using small research reactors. So you use this spectrum and then you do inversion, reconstruct the corresponding spectrum of neutrinos. So there is a kind of problem with this method because that produces some smoothing of the spectrum because you smooth by doing this inversion. But a real spectrum is even spiky, it has some lines even somewhere. That's very non-trivial stuff. In the early days, it was not a big problem with this spectrum, as you will see. But nowadays, when people are doing precision measurements with reactor neutrinos, that becomes a big issue. And some problems, some kind of, how to say, some indications of people are saying new physics have been obtained using atomic reactors. I will discuss a little bit this later. Okay. Now let me say a few words about scintillator detectors. Now let me again repeat what I was already saying. You see, I believe that really to understand the physics, you need to understand how things were obtained, how it was developed. And for this, I'm also discussing these detection methods and how we see neutrinos, how we are getting information about elementary particles, in this case about neutrinos. And during my course, I will again discuss various methods of detection of particles. So what are these scintillator detectors? The key point is that particles which we are studying, like in this case, have the energies in MeV range or even higher. So you have neutrinos with energy 3, 5 MeVs. They interact with protons and produce electrons or positrons with energy around this few MeVs. One way to detect these neutrinos, these particles, say in MeV range, and those are gammas or electrons and positrons, is to convert them into low energy radiation, somewhere in keV range, and detect this radiation using photo effect. Why do you need to convert this in keV range? The point is that the energy levels in atoms are around, say, keV. And photo effect is more efficient when you have gammas or X-rays of this energy in keV range. Not MeV, but in keV range. So you need to somehow convert high energy photons and electrons into low energy radiation in keV range. And this is difference by a factor of 3 orders of magnitude, something like this. And then this can be efficiently detected. So what has been found that there are some special materials, actually something which you are using for washing machines. That's good material to do this conversion. Some materials which have C, N, and M composition, some molecules which contain carbon and nitrogen. I have somewhere this number, but I don't think it's important. So some 8 here, 10 here, or something like these molecules which have this composition. So when you have this material, and it's not expensive actually material. Oh, there are some special scintillators which are quite expensive. So if you have this material, and for instance you have gamma, a photon of high energy, MeV energy, which enters this material, it excites these molecules, and then the excitation of these molecules produce gammas of lower energies in keV range. So keV range. So if this guy is MeV range, it produces many lower energy photons. There are different types of actually scintillators. There are also organic scintillators. But anyway, so the mechanism is that you convert high energy photons into low energy photons. And then you put here photomultiplier. This is what we call PMT. If you do particle physics, you will meet this every time. PMT. Which actually very efficiently detects these low energy photons using photo effect. So how photomultiplier works? Let me draw it again. You can find different shapes of this stuff. So, a low energy photon, the keV range photon, enters here, and here we have photocathode. It interacts with photocathode and produces electron due to photo effect. Now here you have the plates with positive charge, so that electron produced here accelerates, here's plus, 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 with increasing potential. So it accelerates here and produces several secondary electrons, then hits another plate which produces even more, and then even more, and then you detect this signal. You will have big pulse current here. And this technique is extremely widely used in particle physics. Now, scintillator detectors can have a quite big mass. In the first experiment, it was just less than 1 ton. But nowadays, people are discussing 50 kiloton detector, 100 kiloton detectors. which uses such a technique, scintillator detectors.
Whose mass is this? What mass are we talking about for kilotons?
Well, it's the material here, scintillator.
The CNNM.
Scintillator, yeah. Well, Borexino detector, for instance, which works nowadays in Gran Sasso here in Italy. In Gran Sasso laboratory, it has something like 300 tons of scintillator. Now, so we discuss now the experiment on the detection of neutrinos, and this is a Reines-Cohen experiment. And I should say that Marc de Rolo Bruno Pontecorvo, who actually thought a lot about how to detect neutrinos, and he precisely was trying to find some sources of neutrinos and methods of detection. I will come back to this later, but one of the ideas was to use neutrinos from the sun to detect neutrinos in the first place. But then he realized that the energies of these neutrinos are too low to have this detection. But then he invented a technique that still detection of solar neutrinos was possible, which is a so-called Chlorine-Argon method, and we will discuss this later. So people also discussed to detect neutrinos from explosions, of nuclear explosions. And actually Reines was trying to do this in the first. But eventually, so that method which actually led to discovery of neutrinos. Reines and Cohen have two series of the experiments starting from 1953, and the final was in 1956 when he has published, they published a final result. So they used the reaction, let me write it again, of inverse beta decay. And actually, even now people are using this reaction. This is the most important reaction which people are using in reactor experiments. This reaction actually has threshold. And the threshold is 1.8 MeVs. What is this? The point is that the mass of proton is a little bit smaller than the mass of the neutron. Neutron is a bit heavier. And therefore you cannot produce, and also you need to produce electron, right? So you need to have large enough energy of neutrinos for this reaction to proceed, and this is threshold. So the energy of neutrino should be bigger than 1.8 MeVs, again, which includes difference of masses of proton and neutron and the mass of the positron. The experiment was in Savannah River plant. Savannah River reactor. And the sketch of the experiment was the following. The target was water, because water contains protons, right? Almost free protons. So water. And there were two tanks of water surrounded by scintillator detectors. So the size of this detector was 1.8 meters. Here, 1.3. And that was 0.6 meters. And the tank of water was 7 centimeters each. And here is 7 centimeters each. At the borders of scintillator detectors, there were photomultipliers. I will show you some pictures of this, which actually detected the signal which appears in these detectors. So this is PMT. So what is the signal? They have this detector quite close to the core of the reactor. So neutrino passes through the detector, and only a very small part of these neutrinos, so most of them just pass through without any interaction. Some of them in water produce reaction of inverse beta decay. And in this experiment, both products of this reaction, neutron and positron, are detected. So the signal consists of the following two elements. One is positrons. So one is prompt signal. Let me say prompt. Produced by positron. So here, what we have, production of positron and neutron. Positron quite quickly loses the energy and annihilates with electrons present in the medium and produces two gammas. So here is annihilation, and which produces two gammas. Then these two gammas are converted, and they have energy, say, half MeV or something like this. They are converted into low energy photons, as we discussed before. And those photons are detected by photomultipliers. Also, there are photomultipliers here. So all the detectors are surrounded by photomultipliers. So these photons produce soft radiation, and then this radiation is detected by photomultipliers. So another signal is delayed one. And this delayed signal is produced by neutrons. By the way, what is filled in here is water. And cadmium salt has been added to water, plus cadmium chlorine 2. So cadmium salt. Nowadays people are using also gadolinium for this detection of neutrino. So what neutron is doing? A neutron actually, it's a nasty object because it is chargeless, and so it actually has many scatterings. But cadmium is nice because it very efficiently captures the neutrons. Not even water, not water, but cadmium most probably. And so a neutron interacting with cadmium nuclei produces cadmium in excited state, which then decays with emission of gammas, many gammas actually, several gammas. So the signal is delayed because there is some time when the neutron moves inside the detector before it is captured by cadmium. And so the event which we are observing consists of two pulses. One is produced by positron, and then delayed one, and the bigger one. This is electric pulse, and this is time. And these two pulses are separated by something like 1 microsecond, which is 10 to the minus 6 seconds. This is typical time a neutron travels before being captured by cadmium himself. Oh, sorry, this is 10 microseconds. So that's 10 microseconds. Separation of time. 10 microseconds. So one is a signal which is not a big intensity, another one big intensity, and this is because we have many gammas and they are even have higher energy than in this case, because in this case the energy is something like 0.5 MeVs. This is what we call signature of the event. And as usual, experimentalists are fighting with background. So they observe these events, but then you need to prove that this is due to a neutrino interaction, and not just for instance by cosmic radiation. We always have around big flux of cosmic radiation, and also the flux from the walls of the detectors, from the Earth, and you need to prove that your signal is above background. Even background can accidentally produce for you such an event. So that was computed. What is the number of expected background events? And the result is that they saw these type of events above the background. So that was the main conclusion. Questions?
You said that the positron has much lower energy than the neutron, and so it has lower cross-section and probably should take more time to interact than the neutron.
No, but this is charged particle, and you see these are electromagnetic cross-sections here. So they are bigger than neutron. Neutron interacts due to strong interactions. Strong interactions are short-range interactions. So in spite of strong interactions of neutrons, the total cross-section for positron is much bigger. So it's very quickly, so it loses the energy and then captured by electron, which is around. More questions? But I want to stress again that in contrast to Thomson experiment, where it was kind of simple, right, setup, he just saw these flashes on the screen and immediately, inferred some information. Here is already very complicated, chain of logical steps and kind of modeling. Because we have atomic reactor, so what does it mean? So there's uranium, thorium, uranium, plutonium, they put this into the reactor, they have some neutron flux, okay. And then in some detector, which is staying, say, 10 meters from the reactor, people see this type of events, electric pulses. And you see how long is already chain. So we need to have this model that nuclear reactors, there are beta decays produce neutrinos. These neutrinos propagate, have these interactions, inverse beta decay interactions, produce electron, positron, produce neutron. This electron annihilates this proton, this neutron is captured by cadmium, again produces these gammas. These gammas are converted to low energy X radiation. This X radiation produces photo effect. This photo effect in photomultipliers produces enhanced signal, and then what we are detecting is this. So it's not like immediately, one step. So it's a long step, and you can ask, are we sure that this is really what happens? So each step you can ask the question, are you sure that, say, atomic reactors produce neutrino flux? Or are you sure that neutrinos have these interactions of inverse beta decay? So If you think about this, it's kind of amazing, right? And we can compute what is the number of events, number of pulses. So what we see is really electric pulses of this type, separated by 10 microseconds. One is smaller, another is bigger of size. Yeah?
Couldn't there be another sources of triggering the gamma radiation scintillators or any other positron or electron radiation from water?
Yeah, this is what I'm saying. This is what we call background. Yes, and
So
there are photons. Yes, sure. And again, the criteria is that can you accidentally, and they are always producing this event, can you accidentally produce this type of events? So two pulses, one is smaller, another is bigger, with this difference in time. So you may see, so if you look at some kind of recorders, you may see just like this pulse, then after some long time you might have some bigger pulse, and then some small phase. They are just detect this routinely, these things. But then suddenly, among all these kind of garbage events, you see this kind of block of pulses.
Do they see it directly, or do they manipulate the data subtracting the background pulses?
No, they just record everything. So you see, we have this detector. And every gamma which enters produces some pulse. They cannot separate this. They can put some screening of us. But still, you may have some even neutrons which are penetrating, which are kind of, you have always some kind of flux of neutrons which penetrate the detector and produce this.
But this pulse shape and distance in time is a signature.
Yes, this is what we call signature, yeah.
Only
If you would just say, detect only this signal, I don't think that, that we are able to claim that this is something from it. And number of events is not big, so there's something like 50, 30 events of this type of events have been detected in the series of experiments. So, bottom line, that was discovery of neutrino. You know how, again, it's not direct, but so many steps and a lot of modeling or understanding is behind this discovery, right? Reines got Nobel Prize in 1905 for this discovery. Surprisingly, maybe, it was the prize after Nobel Prize for discovery of the second neutrino, muon neutrino. Partially it was, people are saying, because Reines changed his result. So first he got this number of events and compared with expected number of events. This is also very important. You need to see number of events which actually corresponds to what you expect. And you will have exercise to compute this number of events. So, and the claim is that he has observed number of events which is in agreement with what is expected. This is important criteria also. But then it turned out that a number of events was computed not correctly. And Reines then changed his conclusion, saying, oh, yes, we actually have a different number of events detected. And that produces very bad impression, right? So it was first found the mistake in computations, in theoretical computations of the number of events. And so he changed the result. People are saying that was the reason why he didn't got Nobel Prize much earlier. By the way, we will discuss almost all Nobel Prize discoveries, and you can actually study this particle physics working along these stairs. You know, you have these pictures of Nobel Prize laureates, and you can just put up. We already studied this marking. The next one. What I want to finish, what I want to say, finishing this this lecture, is that the studies of neutrinos from atomic reactors is actually a very active field, and it continued all these years. And actually, We are planning some experiments in future, in say, in 10 years or so, so that this is why I had discussed this in some detail. So what are follow-ups? So what happens later? Let me put here. There were a number of, big number of experiments. Let me spend just 5 minutes, man, so I'm sorry for this. The experiments in Gösgen, France, Bouget experiment, France. France has many atomic reactors, this is why that's active in France. Then in Russia, Krasnoyarsk. Then experiments like shoes in France, again, Palo Verde in US. So what were the goals of this experiment? These were experiments in the 80s and 90s. And the goal was to study neutrino interactions, neutrino-nucleon, also neutrino-electron interactions, and then search for oscillations. Search for neutrino oscillations. And neutrino oscillations is the process when, in the course of propagation, neutrino change its identity. So say you produce electron neutrino, then it is transformed by to muon neutrino, tau neutrino. This is what we will discuss later. So the searches were negative, although there were some claims that probably, so in one of these experiments, experimentalists claim that they see some oscillation effect. The important was Kamlan experiment in Japan, and they have discovered neutrino oscillations with so-called 1-2 mixing. And 1-2 split. So we have 3 neutrinos now discovered. So 1, 2, 3, and the mass difference between the first and the second neutrino has been, oscillations with this small mass difference has been discovered by Kamlan experiment. And actually in this experiment, they detected the fluxes from all atomic reactors in Japan. So something like about 100 different reactors contributed to this signal. So this is discovery of 1-2 mixing and 1-2 split. That actually led to a solution of the solar neutrino problem. Next series of the experiment was discovery of 1-2 oscillations with 1-3 mixing and split. So if you have the spectrum of mass of this type, oscillations due to this mass split and mixing have been discovered by Kamlan, and by this, by a series of the experiments, 3 actually, double shoes. It's kind of continuation of shoes experiment. Then diabate in China, which actually gives the most precise measurements of 1-3 mixing and mass split, and Reno in South Korea. So this is discovery of all this 1-3 mixing. Nowadays, people are using these reactor experiments also to search for new neutrino species. Sterile neutrinos, what we call them. One of the latest results was published just a few months ago by a neutrino 4 experiment with a claim that they see some oscillation effect, but most of these claims actually disappear after some time. Finally, let me mention experiment Juno. Under preparation, it will start in 2021-22, and the goal of this experiment is to establish mass hierarchy of neutrinos. So to say, we have such a possibility, but also this one is not excluded. When two states with very small split are up and one isolated is down. So this here's 1, 2, 3. So that two possibilities refer as two different hierarchies. This is inverted and this is normal, which is kind of fundamental importance. And that Juno experiment, again in China, aimed at this discovery.
1, 2, 3 here means like
mass states.
Muon?
No. So it's mass states, and muon, electron, and tau neutrino are mixtures of these states. This is what we will discuss later. So, for instance, this state is approximately half of muon neutrino, half of tau neutrino, and a little bit electron neutrino. So this is the essence of mixing, that mass states do not coincide with states which appear in interactions. Electron neutrino is some state which actually is produced in beta decay together with electron. Electron neutrino has no definite mass. It's actually a combination of three mass states. And for this reason, this leads to oscillations of neutrinos.
This does not happen in other elementary particles, like electron, muon, and tau, for example.
Well, these are, you cannot say that, you see, electron, muon, and tau mark for us neutrinos of a given type. So you can ask if something like this happens in quark sector. Yes, it happens in quark sector. In quark sector, we have mixing and also oscillations like K0, K0 bar oscillations.
But in terms of quark level?
Well, K0 is meson, it's mesonic. It is not a quark. K0 is meson, which is the composite state.
At meson level, we also have that type of oscillations?
Which is actually induced by mixing. We'll have lectures on this. Yeah.
Is there plans to detect cosmic neutrinos?
Oh, they are detected already.
They detected like this cosmic background of neutrinos?
Oh, so these are not detected.
It's
directly.
very difficult.
Okay, so high energy cosmic neutrinos are detected. Astrophysical, if you want.
Okay.
But not from the early universe.
Is it a plans to detect?
Oh, people are working on this. Yeah, that would be fantastic to detect this. Well, I'm kind of working on neutrino physics almost all my life, so if someone wants to have some project on neutrinos, you are welcome. Now let me do the following. I have prepared this, the first exercise. Please distribute. And I would ask you to give me back your solutions on Monday. Yeah, something like this. I think I printed. And I promise that we will meet, but maybe not this time. So I will usually asking two people come to my office and so a chat, as I said. And on Thursday we also have some lunch, right? So which means that we will do this on Friday for the first time. So okay.